Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from Jammu. Today we are going to discuss about a module which is entitled as Evolved Construction and Vector Form of Bragg Equation under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. Explanation of evolved construction, significance of reciprocal lattice in X-ray diffraction, geometrical and construction for Bragg's law, and vector form of Bragg equation. Let us first talk about evolved construction. The methods of analyzing X-ray diffraction data are based on the shape and size of the direct lattice of the direct cell of crystalline matter. However, the data, particularly single crystal diffraction data, are more conveniently handled in terms of the reciprocal lattice and evolved sphere concepts introduced in 1921 by P. Ewald. The reciprocal lattice, as has already been explained, in an extension of Miller index notation for crystallographic planes, which is constructed by erecting vectors from an arbitrary origin within the crystal, perpendicular to the various crystallographic planes in the direct lattice of length sigma HKL, given by sigma HKL equal to K upon dHKL, where K is a positive constant, usually taken as unity, but sometimes the X-ray wavelength lambda being used. It is therefore very essential and important to understand the significance of reciprocal lattice in X-ray diffraction. During our discussion on reciprocal lattice, it has been established that crystal lattices and reciprocal lattices are related through equations 12.9 to 12.11 of section 12.2 and 12.38 to 12.40 of section 12.4 in module 12. While the crystal lattice is a lattice in real space, the reciprocal lattice is a lattice in Fourier space, which is governed by the equation exponential of I pi capital G small r is equal to 1, which is given as equation 13.1, where G stands for the reciprocal lattice vector. In the direct crystal lattice, the points are given by R vector equal to HA vector plus KB vector plus LC vector, given as equation 13.2, where H, K, L are integers. The reciprocal lattice points or reciprocal lattice vector capital G in Fourier space is given by G vector equal to H prime A star vector plus K prime B star vector plus L prime C star vector, where H prime, K prime and L prime are integers. The scalar product of direct lattice vector and the reciprocal lattice vector G vector dot R vector is equal to H prime A star vector plus K prime B star vector plus L prime C star vector dot H A vector plus K B vector plus L C vector, which is equal to H prime H plus K prime K plus L prime L, which is also an integer. Referring to equation 7.4 of module 7, we learn that it is only when three equations are satisfied for integral multiples of H prime, K prime and L prime that we can obtain strong diffracted beam. One can summarily put the significant points as follows. Number 1. The X-ray diffraction pattern of a crystal is a map of the reciprocal lattice of the crystal in the same way as we look at microscopic image as a map of real crystal structure. In a crystal there is a periodic arrangement of atoms, and the atoms are associated with electrons. Reciprocal lattice is a concept that makes us to understand the main mechanical behavior of electrons in a periodic crystal lattice. Consider a diffraction of X-rays from HKL planes with interplanar spacing as dHKL incident at a glancing angle theta HKL. Then Bragg equation can be written as dHKL sine theta HKL is equal to lambda, or sine theta HKL is equal to lambda by 2 into dHKL. We may now imagine construction of a right-angled triangle with one side lambda by dHKL and 2 as its hypotenuse, and inscribe such a triangle inside a circle of unit radius as is shown in figure 13.1a. Figure 13.1ab shows a construction of right-angled triangle with one side lambda by dHKL and 2 as its hypotenuse inscribed inside a circle of unit radius. The operation can be explained through figure 13.1b as follows. The diameter of the circle is the direction of the incident beam of X-rays. Through the origin of the circle, draw a line parallel to LQ. This line makes an angle theta HKL with the incident beam, and as such it represents a crystallographic plane HKL that follows Bragg condition of diffraction and giving theta HKL as the Bragg angle. Now connect points P and Q through a line PQ which makes an angle theta HKL with the crystal plane. PQ therefore represents the direction of diffracted beam. The line OQ represents the reciprocal lattice vector to the reciprocal lattice point Q, which falls on the circumference of the circle. The reciprocal lattice vector sigma HKL originates from a point on the circle where the direct beam leaves the circle. In the three-dimensional case, the circle will turn out to be a sphere. If the sphere, known as evolved sphere, does not pass through any points, it will suggest that the particular wavelength in question will not get diffracted by the crystal in that orientation, and readjustment of orientation will have to be carried out for diffraction to occur. Now, X-ray diffraction can occur if lambda is greater than 2a, because a sphere with radius PO less than 1 upon 2a cannot pass through any point on the lattice, and as such, the above said construction cannot be done. The relation of the reciprocal lattice to the direct space lattice is such that the planes in the one are perpendicular to the rows of points in the other, and the plane spacing is 1 is 2 pi times the reciprocal point spacing in the other. The general reciprocal lattice vector capital G has magnitude twice pi upon d, where small d represents the spacing of planes of Miller indices HKL of the direct space lattice. This is known as evolved construction. On rotating a crystal, both the direct lattice as well as a reciprocal lattice get rotated. It is also learned that while vectors in the direct lattice have the dimensions of length, they have the dimensions of length raised to -1. In the reciprocal lattice, considering direct lattice, the interplanar spacing d is related to the glancing angle theta and the wavelength of X-rays through Bragg's law, given as 2d sine theta is equal to lambda. This law can be expressed in reciprocal lattice as well, which is of the great significance so far as crystallography is concerned. Let us consider a set of parallel and equidistant lattice planes around O, which is the origin, as shown in figure 13.2a. The X-ray beam is incident, say along LO, making an angle, say gamma, with a set of parallel planes represented by XX prime and lines parallel to it. The interplanar distance is d as shown in the figure. To construct reciprocal lattice points for these planes, we choose the constant of proportionality, or what is called as magnification factor, for the sake of convenience as lambda, so that the reciprocal lattice point Q along OR, which is perpendicular to the set of planes XX prime, is at a distance lambda by d from the origin O. Therefore, OQ is equal to lambda by small d. Now a point capital P, which is at a unit distance from the origin O, is taken as center of a circle of radius OP. Therefore, capital LP is equal to capital PO is equal to 1. Let us assume that the reciprocal lattice point Q is located on the circle of reflection. In that case, the lattice planes represented by the reciprocal lattice point Q are appropriately oriented planes for Bragg reflection. Referring to figure 13.2a, angle LOX is equal to gamma, angle OQL is equal to pi by 2, angle QPO is equal to gamma. So LOQ is a right-angled triangle. Therefore, sine gamma is equal to QO upon LO is equal to lambda by d upon 2, or sine gamma is equal to lambda by 2d, which is given as equation number 13.3. According to Bragg's law, the planes are appropriately set for diffraction if 2d sine theta is equal to lambda, or sine theta is equal to lambda by 2d, given as equation 13.4. From equations 13.3 and 13.4, we find gamma equal to theta, which is given as equation 13.5. It suggests that the set of planes which are parallel to XX prime and identified by the reciprocal lattice point Q satisfy Bragg law. Now P is the center of the circle and PQ is the line. joining the reciprocal lattice point to the center of the circle. PQ is parallel to the direction of reflection OM. It means that the lattice planes are appropriately oriented for Bragg diffraction if their reciprocal lattice point lies on the circle of reflection. The direction of diffraction is given by the line joining the origin to the reciprocal lattice point. This circle is therefore known as circle of reflection, which, if considered in 3 dimensions, will be substituted by a sphere. The above said construction by evolved, and the above described sphere of reflection is named after him as evolved sphere. Figure 13.2b represents the geometrical construction for Bragg's law as shown in a different way. Considering the triangle OPQ of figure 13.2b, let the incident X-ray beam PO be represented by the vector S and the diffracted beam PQ by the vector S prime. From triangle OPQ, we have OQ vector equal to S prime vector minus S vector equal to delta S vector. OQ vector is equal to R star vector, which is equal to D star, where OQ represents the reciprocal lattice vector. OQ vector is equal to modulus R star vector is equal to modulus D star vector is equal to 2 sine theta. For the sake of convenience, 1 by lambda is used instead of 1 as the radius of the reflection circle and constant of proportionality capital M as 1. Thus we have delta S vector equal to modulus R star vector equal to modulus D star vector is equal to twice sine theta by lambda. Vector form of Bragg equation. Crystal, as we know, has a regular arrangement of atoms, and there are a large number of free electrons, particularly more so in metallic crystals. The motion of free electrons more or less resembles the motion of molecules of gas. The periodicity of lattice, however, affects the dynamics of free electrons. When atoms are brought together to make a crystal, we have allowed energy bands separated by forbidden bands. The forbidden energy gaps arise because of the Bragg diffraction of electrons from the lattice planes of the crystal. Electrons are associated with wave-like character and get diffracted from crystal planes in almost the same way as X-ray do. The reciprocal lattice concept can be easily applied to interpret diffraction effects of electron waves. In the discussion on application of reciprocal lattice concept to solid-state theory, it is convenient to take the proportionality constant, or what we call as the magnification factor, of the reciprocal lattice to be equal to 2 pi instead of 1. Therefore, we can use expressions of earlier section regarding reciprocal lattice with the magnification that a factor of 2 pi is used. The new expressions, which are based on equations given in module 12 regarding reciprocal lattice, are A star vector is equal to 2 pi into B vector cross C vector upon A vector dot B cross C vector. B star vector is equal to 2 pi dot A vector cross C vector upon A vector dot B cross C vector. C star vector is equal to 2 pi dot A vector cross B vector upon A dot A vector dot B vector cross C vector. All these are grouped under equation 13.6. A star vector dot A vector is equal to B star vector dot B vector is equal to C star vector dot C vector is equal to 2 pi, given as equation 13.7. Similarly, A star vector dot B vector is equal to A star vector dot C vector is equal to B star vector dot A vector is equal to B star vector dot C vector is equal to C star vector dot A vector is equal to C star vector dot B vector is equal to 0, which is given as equation 13.8. The reciprocal lattice vector G HKL vector, which is similar to R star vector HKL or D HKL star vector, is given by the expression capital G HKL vector is equal to H A star vector plus K B star vector minus L C star vector, given as equation 13.9. So G HKL vector is equal to twice pi R star HKL vector. Having explained the geometrical construction of Bragg's law using evolved sphere in the theory of solid state is discussed in a way similar to the one as already described. K vector is taken as wave vector of the incident wave and K prime as the wave vector of the Bragg diffracted wave, as is shown in figure 13.2b. Radius evolved sphere is taken as twice pi by lambda. Modulus of K vector is equal to modulus of K prime vector is equal to twice pi by lambda. The Bragg diffraction condition can be expressed as K prime vector minus K vector is equal to delta K vector is equal to capital G vector. In the previous section, it was shown that delta S vector is equal to twice sine theta by lambda. However, in the present case, we have used modulus of K prime vector equal to modulus of K vector is equal to twice pi by lambda. Delta K vector is equal to twice sine theta by lambda into 2 pi, or delta K vector is equal to 4 pi sine theta by lambda. Now K prime vector minus K vector is equal to G vector, or K vector plus G vector is equal to K prime vector, or we can say K vector plus G vector whole square is equal to K prime square. K vector plus G vector dot K vector plus G vector is equal to K prime square. K square plus twice K vector dot G vector plus G square is equal to K prime square. However, modulus of K prime vector is equal to K prime. Modulus of K vector is equal to K, and modulus of G vector is equal to G. Since K is equal to K prime for Bragg condition, we have twice K vector dot G vector plus capital G square is equal to 0. This is the vector form of Bragg equation. So students, let us summarize what we have learned in this module. We have learned about the significance of reciprocal lattice in X-ray diffraction. We have learned about the concept of evolved construction. The sphere of reflection, known as evolved sphere, is described. Geometrical construction of Bragg's law using evolved sphere in the utility of solid state is described. Equations expressing the vector form of Bragg equation have been derived. Thank you.